quantum mechanics.
Do you two know how scientists identify the substances in distant stars? Do you know how we measure the composition of the sun, for example? Sure. One major tool is spectral analysis, isn't it? Yes, indeed.
I am familiar with the results of spectral analysis, but I am a bit unsure of how the spectra arise to begin with. Chaucer, is that part of our material for today?
Yes, it is, Diana. In fact, it is the starting point. Let's use Professor Peabody's Wayback Machine, since we don't have one of our own, and look at a little science history. Jeeves?
Traveling to the 1750s, we find that scientists were putting different substances in flames and passing the resultant light through a prism. They found that the hot gases given off by the burning materials emit different colors of light or spectra. For example, ordinary table salt generated a bright yellow spectra. Furthermore, not all the colors of the rainbow appeared. There were dark gaps in the spectrum. In fact, for some materials, there were just a few patches of light. By the 1820s, they recognized that spectra provided an excellent way to detect and identify small quantities of an element in a powder that was put into a flame. Meanwhile, the white light of the sun was also being examined closely. And in 1802, it was discovered that the solar spectrum itself had tiny gaps. There were many thin, dark lines in the rainbow of colors. But the reason for spectral lines in the light and the relationship to each substance was a real mystery. Traveling forward from that era to a little over 100 years ago, scientists were examining the colors of light given off by solid heated objects. They discovered that these hot solids gave off continuous spectra, and that the overall color of the light revealed the temperature of the object. Now, this was important because scientists realized that this discovery made it possible to measure the temperature of an object from a distance. They could measure the temperature of the sun, for instance. During these discoveries, they also noticed that some of the objects absorbed light extremely well, almost perfectly in fact. They were called black bodies because they absorbed virtually all the light that was shown upon their surfaces. These same objects also radiated almost perfectly, and as noted before, the temperature of the black body object determined the distribution of colors or wavelengths in the emitted light. This curve shows how much light of each color is emitted by a cool object. As you can see, there isn't much light, and what light there is mostly lies out past the red end of the spectrum, in the infrared. The figure on the right will show the different colors added together as we progress. Right now, only red light is visible. This curve shows how much light of each color is emitted by a medium temperature object. And the most light is emitted in the orange, yellow, green wavelengths. So now we add orange, yellow, and green to our cauldron of light on the right. As you can see, the combination so far looks yellow. This third curve is for a really hot object. Lots of light, and with most of it being emitted toward the blue end of the spectrum. And as you can see, our cauldron now is pure white in the center where all the colors overlap. A heated black body follows this color path as the temperature rises. A good example of black body radiation is the heat inside a kiln. Inside the kiln, electromagnetic radiation, light and heat, exist in a form of standing waves. Waves that, like the vibration of a guitar string, are attached at both ends. The ends of the standing waves, like the ends of a guitar string, do not move. They are anchored to the sides of the kiln. And many, many waves exist with varying wavelengths of color. At low temperatures, the primary color inside the kiln is the infrared, and we cannot detect it with our naked eye. But as the temperature rises, the kiln begins to glow red, and as the temperature continues to rise, the dominant color changes to orange, then yellow, then bluish white. The distribution of energy in light shifts to shorter wavelengths as the temperature rises. But there was a problem. The scientists expected the distribution of emitted light to continue to the increase at wavelengths toward the ultraviolet end of the distribution. It didn't. Instead, there was less and less light given off as they were further and further into the ultraviolet. This was called the ultraviolet catastrophe. But it wasn't a catastrophe at all. It was the beginning of something remarkable. A truly great scientist named Max Planck soon figured out a way to explain the observation. He concluded that the energy contained in the standing waves inside the kiln did not and could not possess just any and all different amounts of energy. Instead, the quantity of energy these standing waves possess had to be limited to a few specific discrete values of energy for each color. A standing wave of blue light, for example, can have energy equal to 0 electron volts, or 3 electron volts, or 6 electron volts, or 9 electron volts, and so on. In general, energy equals any whole number, n, times Planck's constant, h, times the frequency of light, nu, which for blue light is any number times 3 electron volts. But notice, blue light standing waves cannot contain energy equal to 1 electron volt, or 2 electron volts, or 4 electron volts. Realizing that energy could have only discrete values was the beginning of quantum mechanics. The energy is said to be quantized, and n, from the equation above, is called a quantum number. Planck's conclusion that light energy is quantized was quickly used by Einstein to explain another puzzling phenomenon. It was known that shining a light upon a metal plate can release electrons from the plate. But the light has to have a certain wavelength before a single electron is released. We can shine brighter and brighter light on the plate forever, but if the color isn't right, the electrons stay home. Einstein concluded that the light striking the plate had to be coming in discrete bundles, and unless a single bundle had enough energy to free an electron from its captivity, it would remain trapped. And as Planck has suggested, the wavelength and frequency of the light was a measure of the amount of energy each bundle carried. So while blue light packets might be able to free an electron, red light packets could not, no matter how many red packets hit the plate. But wait a minute. That sounds awfully like light is a particle and not a wave. And there are mountains of data showing light behaving like a wave. Diffraction, refraction, interference. Which is it, a particle or a wave? It is both. These light packets are extremely tiny. Let's call them photons, from Photos, the Greek word for light. And when you try to explain the behavior of things this small, you must resort to really unusual ideas. The ideas contained in quantum mechanics.
Now let's see how quantum mechanics helps us to understand atomic structure. Ah, Bohr and de Broglie are two of my heroes.
Boron who?
Cute, Diana. Cute. Jeeves?
It was during the early decades of the 19th century that the structure of atoms was coming into focus. It was known, for example, that a hydrogen atom contained one proton and one electron. But the scientists of the time could think of no stable arrangement of the two particles. It was known that a proton and any atom were grouped in a small central region called the nucleus, and that the electrons were somehow arranged in comparatively large distances outside the nucleus. But in hydrogen, if the electron were stationary, it would fall into the nucleus since the charges on the particles would cause them to attract one another. Yet the electron couldn't be in orbit circling the nucleus either. Circular motion requires consistent acceleration of circling body to keep it from flying away. But the electron has charge, and charged particles radiate light when they are accelerating. So an electron in a circular orbit would radiate light and would spiral into the nucleus. Niels Bohr proposed the first working model of the hydrogen atom. In the Bohr model, the electron circles the nucleus as if it were a planet going around the sun. And with a nod to energy quantization that Max Planck dreamed up for solving the ultraviolet catastrophe, Bohr said that inside the hydrogen atom, the electron was allowed to have only discrete values of angular momentum in its orbit around the nucleus. Translated, this means the electron can occupy orbits only at certain distances from the nucleus. And Bohr simply dismissed the problem of an electron radiating away its energy by stating that it just didn't happen. Even great scientists cheat sometimes. He postulated that inside an atom, electrons only radiate energy when they jump from one allowable orbit to another. And the energy of this radiation reveals the allowable orbits. The wavelengths of light absorbed by hydrogen when white light is shined upon it, as well as the wavelengths of light when it is subsequently re-radiated, had been precisely studied at the time but never explained. Here's a sample of an absorption spectrum and an emission spectrum. By predicting the value of orbits that an electron could have, Bohr's model also predicted the wavelengths of the lines in the hydrogen spectrum. And his model was tremendously successful. It explained in exquisite detail the atomic spectra of hydrogen. When the energy of the wavelengths of the spectral lines are compared to the energy differences in orbits allowed in Bohr's atom, they agree exactly. So the quantum approach worked well in explaining the allowable orbits. But no one was certain why only those orbits were allowed. In his doctoral dissertation in 1924, Louis de Broglie put forward a simple idea that significantly advanced the understanding of the extremely tiny. a quantum leap forward, you might say. Since Einstein and Planck and Compton had firmly established that light could have the characteristics of both a wave and a particle, Du Bois suggested that matter particles, protons, electrons, atoms, billiard balls, could sometimes act like waves. And when this idea was applied to Bohr's atom, it answered many questions. First, the allowed orbits had to be exact multiples of the wavelengths calculated for the electrons. Other orbits produced destructive interference of the waves, and soon the electrons couldn't exist there. So the circumference of the orbit must equal the wavelength, or twice the wavelength, or 3 times the wavelength, or for that matter, any multiple of the wavelength. Second, these orbits weren't really orbits in the traditional sense. These electrons didn't travel around the nucleus in a circle. Rather, they took the form of a standing wave that surrounded the nucleus entirely. The exact position and momentum of the electron particle could not be specified at any given instant.
De Broglie's particle waves seemed to answer many questions, but this was still not the final answer. No, the final answer is a brilliant piece of mathematics as well as physics. I agree. Jeeves, take it away.
A true giant of quantum revolution was Werner Heisenberg. And from the vagueness of positions of electrons in Du Bois' standing wave orbits, he drew a tremendous insight which he stated like this. The more precisely the position is determined, the less precisely the momentum is known, and vice versa. And while it may sound like a bunch of gobbledygook, it was the insight necessary to understand how an object can be both a particle and a wave. This single statement led to the understanding that subatomic particles can disappear and reappear in another place. And they can do this without existing in the intervening space. When an electron is trapped inside an atom, the places it can disappear and reappear include specific locations around the nucleus. And that makes it look like a shell. Basic particles can also be in more than one place at a time, if the time is brief enough. An electron can travel from here to there along all possible paths simultaneously. And even more astounding, these particles can appear out of the nothingness of space, exist for an extremely brief instant, and then disappear. Scientists call them virtual particles. They may be virtual, but they can have very real effects. All this jumping around makes particle description so inexact. But then existence itself is inexact at these tiny scales. The question is often asked, what is it that is waving when a particle is described as a wave? And after a lot of hem-hawing around the issue, the right answer is, existence is waving. The particle is jumping around, coming into and out of existence. And those places where the wave crests are maximum are the places where the particle materializes, most of the time. While the places where the crests are minimum are the places the particle avoids. The wave is a map of the particle's existence. And as the wave changes, the particle changes as well. While all important ideas necessary for quantum theory were established before him, it fell to the genius of Erwin Schrödinger to to develop the equation that correctly describes the motion and behavior of all things this tiny. While Bohr and de Broglie managed to describe the hydrogen atom, Schrödinger's equation was able to describe hydrogen with the same detail. And then, it could go far beyond. It manages to account not only for the hydrogen atom, but it describes nothing less than all the atoms and all the elements in the universe. Schrödinger's quantum mechanics explains every element in the periodic table of the elements. The solution to Schrödinger's equation, called the wave function, is a fantastically accurate description of the real world.
Schrödinger's equation is really cool.
Yes, it is, Diana. I agree, but can we talk a little more about Heisenberg's uncertainty principle? Isn't there more to consider than the approach we use to describe it? Certainly, Kevin. Jeeves, let's have a closer look at that, please.
Werner Heisenberg did more than make a quantitative statement when he said that the particle's position and momentum could not be known simultaneously. He wrote an equation that quantified the relationship. Let's see how that information can lead to an easy understanding of the hydrogen atom described in exquisite detail by the Schrödinger equation. Without going into too much detail, let's look at a proton and an electron. Since the electron has a very tiny mass, it can occupy a very large region of space. Conversely, the proton has a very large mass, 2,000 times that of an electron, and therefore it occupies a very tiny region of space. The result is a quantum mechanical hydrogen atom, a tiny massive nucleus surrounded by a much larger cloud representing the electron. If we look at a simple graph relating the probability of finding the electron in a shell at a given distance from the nucleus, we find that as we travel outward from the nucleus, the probability increases at first as the shell expands. It reaches a maximum value and then decreases again as the electron cloud thins to almost nothing at large distances. Amazingly, the radius where the probability reaches a maximum is precisely equal to the radius of the first allowed orbit of Niels Bohr's model of the hydrogen atom. And its energy is exactly equal to the energy of an electron in this orbit in the Bohr atom. So this is a very good picture of a hydrogen atom with an electron in the lowest energy state. The electron occupies a cloud instead of an orbit, but it spends most of its time at the radius predicted as an orbit by the Bohr model. It also spends most of its time possessing the energy that an electron in that orbit would have. But of course, the atom is not always found in the lowest energy state, as there are other orbits allowed in Bohr's model. There are other higher energy states in the quantum mechanical hydrogen atom. These states are defined primarily by the quantum number n that we talked about earlier. And for each state, the electron has a different energy, which results from the shape of the electron cloud. For n equals 1, called the ground state, the shape is a symmetric cloud, the same in all directions. For n equals 2, the shape can take two forms, although both shapes have the same energy. One is a double spherical cloud, one sphere inside the other, while the other shape for n equals 2 is in the shape of a dumbbell. For other values of n, the shapes can be pretty strange, like this torus plus dumbbell shape. An electron in the lowest energy shell in an atom can be struck by and absorb the energy of a photon, giving it enough energy to jump to the next energy shell. And the reverse process allows the electron to jump back down into the lowest energy shell and emit a photon. The color of the photon depends on the energy difference between the two shells. This explains the spectral lines that identify an element. Since white light contains all the colors in the spectrum, when we shine white light on a sample of an element under the right conditions, the atoms absorb all the photons that allow their electrons to jump to other energy shells. So, the absorption spectrum is all the colors in white light minus those that match the difference in energy shells within the atom. And when those electrons spontaneously jump back down to the lowest energy levels, that emission spectrum contains only the lines that match the difference in the energy shells within the atom.
Now it's time to investigate one of the most important properties of elementary particles. One that literally shapes the atoms of each element in the periodic table. Jeeves, please continue.
We have just discussed how Schrödinger's equation shows us how to accurately describe fundamental particles with a wave function. Now let's examine why two electrons together reveal a feature of quantum mechanics totally unlike anything in the large-scale world we inhabit. In a classical setting, even if two things are identical, they are still individuals. As long as we keep track of them carefully, we can treat them separately and label them A and B, or X and Y, or 1 and 2. But consider what is different about a two-electron system. Whether in an atom or in a box, it doesn't matter. Since the two electrons are consistently phasing in and out of existence, and since they are absolutely identical, it is impossible to keep track of specific individuals. Because of this, we must use a combined wave function to describe the pair rather than using two individual wave functions. This new two-particle wave function will have two parts to it, and those parts will either add or subtract. Physicists would say this makes the wave function either symmetric or antisymmetric. And it turns out that only the antisymmetric function works for the electrons, and quarks, and protons, and neutrons. Let's let this red wave represent the first part of the combined wave function, and this green wave represent the negative of the second part. If the electrons are in the same state, these two waves will be a mirror image of one another. As one goes up, the other goes down in perfect synchrony. So when we combine them, we get no wave at all. And since the wave is a map of electrons existing at that point, no wave means no electrons. So clearly, two electrons can never be in the same state, because that causes their combined wave function to disappear. Now, the only components making up the dynamical state in the atom is the shell it occupies, and another property that electrons have called spin. You can think of electrons as little spinning tops, if that helps. And these electron tops can spin in only two ways: upright or upside down, which can make them distinguishable. So the end result is that two and only two electrons can occupy each shell in an atom, one with spin up and the other with spin down. Other electrons in the atom must occupy higher and higher shells. This is called the Pauli exclusion principle, first espoused by Wolfgang Pauli. Without this exclusion, all electrons would occupy the lowest energy state, and atoms would behave very differently, and the universe would be a very different place. The fact is that the property called spin is quantized as well. No big surprise. And all the particles fall into one of two different families because of this. Those particles that have spin equal to 1/2, or 3/2, or 5/2, and so on, form the family called fermions. The name comes from Enrique Fermion, who along with Paul Dirac developed the statistical methods of dealing with them. Fermions are said to have half-integral spin. And as indicated above, electrons, quarks, protons, neutrons are all in this family. The other family of particles have spin equal to 0, 1, 2, 3, and so on. They are called bosons, after Satyendra Bose, who along with Einstein developed the statistics for dealing with this family. Unlike fermions, which must obey the Pauli exclusion principle, bosons do not. Groups of multiple bosons will all gather in the lowest available energy state. Photons, gluons, gravitons all fall into this family. If bosons had to obey the exclusion principle, many modern marvels could not exist. Like lasers, which require that huge numbers of photons be in the same state at the same time, and again, the universe would be a very different place.
Oh, day and night, but this is wondrous strange.
Yes, it is, Horatio. I mean, Diana. Quantum mechanics is different, but so far it isn't too weird. Okay, Jeeves, show us a little weird. Where is the weird?
Where's the weird, you ask? Once you get past existence coming and going, and virtual particles, and uncertainty, and exclusion, most of the weird stuff in quantum physics comes from what is known as entanglement, and subsequently wave function collapse. When two or more particles interact, their wave function becomes entangled in such a way that some properties of each are now depending on what happens to the other particle. Then these particles can be carefully separated, while in careful isolation to distant locations. But as long as they're not disturbed, they are still entangled and still have properties dependent on each other. Then, when one particle is examined to see what the individual property might be, the wave function instantly disentangles. Physicists would say this wave function collapses. Instantly, the other particle has its codependent properties disentangled and determined. Here is an example. We can set up a source to emit electrons in pairs, with their spins dependent on and opposite from one another. Now, neither electron knows what spin state it is in. Both are flip-flopping back and forth between spin up and spin down. But their wave functions are entangled, so that whenever one of the electrons is disturbed and settles into one of the spin states, say spin up, the other electron instantly settles into spin down state. And this instantly occurring collapse happens whether the electrons are next to each other or on the opposite side of the planet. And while some of that is truly weird, a host of modern technologies are beginning to rely heavily on this weirdness. Quantum computing, quantum cryptography, and quantum teleportation, to name a few. And because of the work they are doing in these fields and others, many scientists have little doubt that this particular quantum weirdness is an actual phenomenon. Real entanglement experiments have now been done where the separations have been over 100 kilometers, proving that distance does not destroy entanglement. This is analog. This is digital. This is analog. This is digital. This is analog. This is digital. If it is continuous, it is analog. If it is granular, it is digital. The current trend in audio, video, and communication technologies is to go digital. Instead of a continuum of color in video devices, we are limited to some finite number of colors. Instead of a continuous picture, our photo is divided into pixels. Instead of just any frequency in audio, we are limited to specific steps. This is very much like the universe in the realm of the small. The entire universe went digital about 14 billion years before we thought of it. Space, time, energy, momentum are all granular. There are only certain specific values allowed, and this granularity is accurately described by quantum mechanics.